I'm Will Regan, president and co-founder of Pacific Fusion, and I'm here today to tell you about our plans to develop affordable power using pulsar-driven inertial fusion with net facility energy gain by 2030 and the first power generation by the mid-2030s. There were three major breakthroughs that happened in 2022 that really transformed the fusion landscape. First, as I'm sure you've all heard, the National Ignition Facility used lasers to drive the first controlled fusion ignition, achieving the physical conditions needed for commercially relevant fusion. However, since the NIF's lasers are less than 1% efficient, we still need a more energy efficient way to access these physical conditions. Fortunately, at the same time, Sandia Z facility reported record-setting pulsar-driven inertial fusion results using a much more energy efficient path to get to ignition than lasers. By driving their maglev concept with a pulsed electrical current, Sandia achieved the second highest fusion performance ever, second only to laser fusion. And this maglev approach has the added benefit of using lower complexity targets, which will further ease the path to commercial power. And last, that same year, a team at Lawrence Livermore National Laboratories, led by our now CTO, Keith Lachine, demonstrated an even more energy efficient and mass manufacturable pulse power technology than what's used on the Z facility. This new pulse power technology is called an impedance match Marx generator, or IMG, and this opens up a path to build practical and cost-effective fusion machines. So when you take these three things together, it showed that we can achieve conditions needed for commercial performance, that we can get there energy efficiently, and last, that we can do so with affordable mass manufacturable hardware. So we founded Pacific Fusion in the summer of 2023, building on all these breakthroughs with the goal to demonstrate net facility energy gain, so more fusion energy output than we initially store in the system by 2030, with a path to extend that to the first commercial power by the mid-2030s. In the 2 years since our founding, we've grown the team to over 110 staff and have raised over $900 million in a tranche Series A, where the funding is called as we achieve predefined milestones. In order to achieve these ambitious timelines and milestones, we need to bring together the world's leading fusion researchers with the best engineers and operators coming from hard tech industries. And we've been really fortunate to assemble just such a dream team with folks like Alex Zylstra and Nathan Mizan coming from Lawrence Livermore National Laboratory. They're heading up our experiments and target design teams respectively. We've got folks like CFS vacuum group lead, former CFS vacuum group lead Fabio Ravelli, who's heading up our vacuum system development. We've also got scientists joining us from other industries like Indrani Bhattacharya, who's joining us from the materials industry, working at companies like Scylla and Corning, and she's helping us develop advanced components. And lastly, we've got a lot of great leaders coming from the automotive and aerospace industries, people like Courtney Richardson, who formerly headed up Tesla's Fremont manufacturing infrastructure, and Craig Companion, who recently joined us from Blue Origin, where he led supply chain and additive manufacturing. We're planning on growing the team even more over the next year and a half, and have about 30 openings on our website right now. So I strongly encourage all of you great scientists, engineers, and operators out there, please do reach out, check out these open roles. So with this team and these resources, here's what we're designing and building over the coming years. This is our demonstration system. We'll use this to demonstrate net facility energy gain by 2030. In short, it's a big capacitor bank that's used to deliver an electrical current pulse that rapidly squeezes a small fuel container called the target. This system is about 300 foot across, stores about 80 megajoules of energy, and can deliver over 10% of that stored energy to the target, resulting in ignition and net facility gain. So for us, more than 80 megajoules of fusion output. If we compare this to facilities like the NIF, our demonstration system only stores about a quarter of the initial energy, costs about a tenth as much to build, but we can drive targets to roughly 100x the facility level energy gain of the NIF. So if you look at that overall, it's roughly 1,000x increase in performance per cost. And if you compare us to other major facilities like Z, we can drive over 2x more current through our targets, over 60 mega amps compared to Z's 25 mega amps of peak current. And that's important for us to get the conditions needed to get not just ignition, but facility gain. So here's how the system works. Effectively 3 steps. Step number 1, you charge up your capacitor banks while you load a fuel container in the central fusion chamber at the center of the machine. Step 2 is you discharge those capacitor banks, sending a large electrical current pulse traveling inward along these transmission lines, these wires. And then third, you direct that electrical current to a tiny fuel container, our target, that holds a few milligrams of DT fuel inside. And that electrical current creates a very strong magnetic field that rapidly implodes that can and squeezes the fuel up to fusion ignition conditions and high gain. In our demo system, we'll be taking only about one shot a day and measuring all the output with a sophisticated suite of diagnostics. You can read about some of those diagnostics in our AMPS paper, affordable, maintainable, practical, scalable. It's our technical roadmap we shared on the archive a few months ago and is coming out in a peer-reviewed journal shortly. In a power plant, though, we'd be harnessing that output and using the neutrons to breed more tritium in a blanket. Okay, so I've showed you what we're building to achieve net facility gain by 2030. What else do we need to make power by the mid-2030s? So we actually we'll need to build a new system that looks pretty similar to the demo system. Same footprint, roughly about the same amount of stored energy. The main difference in this new system is that it has to cycle not just once a day, but about once every second or a few seconds. We'll also need to capture that energy output to generate electricity and siphon off a small fraction of that generated electricity to recharge the pulsar and to power other systems. And then finally, we'll need to close all of the material loops. So after every cycle, every target we fire, we'll need to capture and recycle all of the unburnt fuel. We'll need to capture and recycle all of the non-fuel target materials. And we'll need to process the blanket that's catching all the neutrons and breeding tritium and capturing the heat. So as we drive toward facility gain on the demo system, we're ramping up development basically across all of these areas in parallel. And we can't just be content to build one power plant that works. That's not the goal. The goal is to build machines that deliver the world's most affordable firm power. And to do that, we need to be constantly improving, simplifying, eliminating components, accelerating production of every single piece of our system to ensure that it's affordable, mass manufacturable, and maintainable as possible. Our IMG pulse power architecture already lends itself pretty well to these challenges. It's built in a very modular fashion, starting with a small unit called a brick, made of 2 capacitors and a switch. Those capacitors are about the size of a lunchbox, so that's a pretty small unit. You then take about 10 of those bricks and attach them to a common anode ring that forms what's called a stage. And then you add up a bunch of those stages in series to form a module about the size of a shipping container. And the majority of our system is just carbon copies of that module, about 156 in our demo system, similar amount in the future power plant. Yeah, so that lends itself well to mass manufacturing and scale deployment. Certain supply chains do still need to be scaled up, things like fast pulse capacitors, but nearly all of our system is built from low complexity parts and widely available materials, things like metal, plastic, oil, and water that you can source, pretty much everywhere. So that helps keep our capex down. On the OpEx side, O&M costs, we're designing all parts of our system for easy serviceability and long life. And finally, to keep the fuel costs low, we're specifically developing our targets so that they have a path to low-cost mass manufacturing. And this is thanks in part to their cylindrical geometry and fairly low complexity compared to other inertial fusion targets. So we'll share lots in the years ahead, but here's what's most imminent. Like I mentioned, we recently released our detailed technical roadmap. This describes our path to affordable, maintainable, practical, scalable fusion, or AMPS. That's available now in the archive, like I mentioned, and is soon coming out in a peer-reviewed journal. We also recently completed our first set of major milestones that unlocked our next tranche of capital in our Series A, and we're using that to rapidly build toward our first full-scale IMG module. Last I'll mention, we're in the final rounds of site selection for where we'll build our demonstration system. We've narrowed it down to 2 sites in California, Alameda, which is pictured here in a render, and also Livermore, and 1 site in New Mexico in the Albuquerque area. So at Pacific Fusion, we always aim to make the fastest progress that's physically possible. So in that spirit, I yield my last 10.5 minutes, and I really look forward to your questions in the lab session. Thank you.